We ready or what? We're ready. Good. That is great. So, by request, a little poisson warm-up. Let me see if I can remember what the assignment question, it tells you, so it does give you the rate, but it's a little bit weird, right? So it says, I can't even remember what it's about, but yeah, something like that, right? Okay, so just as a little bit of review, so Poisson on assignment 6. Okay, so it gives the rate, and like I said, all the numbers will be different. Let's say for our example, it says, okay, well, there's 12 per 12 defects. 12 defects per, I don't know, 15 yards. All right? So that's going to be your rate. Right? However, then it says, so just as kind of just grabbing numbers out of thin air here, how many defects would you expect to have in 20 yards? Okay. So how many defects in 20 yards or something like that? Does anyone have it?
Mine exactly was you have 12 defects in, or 6 defects in
so
yard or square foot.
How about the probability of 6 defects in 20 yards? How about? Okay, I'm piecing it together. It's good. Thank you. So now we know that we have 12 defects per every 15 yards, right? But what we want is a different type of yardage. And so what we have to do is we have to figure out how many defects we've got per yard and then multiply it by 20, right? So the number of defects per yard, well, we've got 12 defects per 15 yards. Hopefully I picked, well, I guess it doesn't really matter. 12 divided by 15, phew, 0.8 defects per yard. So now in 20 yards, right, our rate is going to be 0.8 times 20. $16 defects per 20 yards. And so that's going to be your lambda. So 16 divided by 20. Oh, hang on. No, 0.8 times 20 is 16. Yeah, we have the same rate. I don't know why I'm pausing. So there's the rate, yeah, our rate is going to be 16 for every 20 yards, right? 16 defects per 20 yards. So that's your rate that you're going to use. So it's a little bit doop, doop, two-step. I don't know, I just feel like that's what I did. Hang on. 12 divided by 15 is 0.8. 0.8 per yard. And then we've got 20 yards. No, so the rate for 20 yards is going to be 16.
Oh, so it's specific to the
Yeah. So the 0.8 is per yard for each yard. But then if we're looking at a 20-yard block, then the rate would be 16 defects per 20 yards.
Okay.
Yeah. Good. So that assignment is due tonight. Make sure you work on that. Okay, are we ready for some new stuff or what? How about more review? No, Heather. All right. So I asked / begged you guys to read 7.1 to 7.3. You did? I did. You were begging? Yeah, I was. So we're a little bit behind, but it's okay. It's okay. We've got time. But so chapter 7 is where things kind of get interesting. So nothing new yet, really. What happens in chapter 7 is we go back to those Z-score questions, right, where I tell you, okay, something follows a normal distribution with a mean of this and a standard deviation of this, right? And so usually we've been talking about individual observations, right? What's the probability that a person is taller than this amount, right? What's the probability of weighing less than this, right? Things like that. So we've been talking about individual observations. Okay, so 7.1, I'll just finish writing it out here. Variability in estimates, this very cryptic header, I guess, for a little bit longer. What we're going to start doing now is, instead of talking about individual observations, right? What's the probability of finding one person that's taller than this, right? Now we're going to start saying, okay, you've collected a random sample of 20 people, right? Which is more likely, right? You've collected a random sample of 20 people from this group. What's the probability that their average height is taller than this amount? And so averages behave very similarly, right? But we're just going to look at how averages behave. And so in chapter 6, we use Z-scores to find probabilities associated with individual outcomes. So in chapter 6, we use Z-scores to find probabilities associated with individual outcomes. Individual outcomes, or I'll say / observations. And in brackets, I'm going to put an X. Okay. So if I just pull in our example, let's do the one that we did together here. Right. Actually, I'm just going to steal the blurb, which hopefully you have. Maybe you. Either way, we're just going to have a read here. Right. All the problems that we were doing, what's the probability of finding a box that weighs more than this, right? What's the probability of finding a box that weighs less than this? What percentage of boxes weigh more than this, right? And so there we're talking about individual outcomes, right? Individual weights. Okay. I'll move this down and say that here, this is from the chapter 6 examples. And I can't remember what the parts were. So I guess I'll just bring them in here. So what's important here is that all of these subparts that we were talking about, right? These are finding probabilities, even though it says proportions, right? But we know probabilities, proportions, percentages, they're all areas under the curve, right? So it doesn't matter what P word we use, probabilities or proportions for individual boxes. Right? So what's going to happen now is we're going to start talking about probabilities associated with mean observations, right? And so now we will start, I'll say finding probabilities. Oops. Probabilities associated with mean observations, mean / average, right? By now, I do assume that you've got those two linked up. We'll start finding probabilities associated with mean or average observations. As far as tackling these problems go, how they're always going to be laid out is we'll still have that first block of information that's the same as for an individual observation, and then I get you to do probabilities with an individual observation, and then I tell you in another subpart, I say, now you've collected a random sample of this size. Right? So now, okay, now you're saying, okay, I'm not talking about individual observations anymore. Now I'm talking about a mean observation, right, X bar. And so, and maybe I should put that in brackets here. Make some room for myself. X bar. So what I'm gonna do is I'm just gonna give you everything that we need, and then we're gonna pick it apart and just kind of dissect it. So if we take a random sample of size n, then we can say, then X bar, right? This is the sample mean, follows a normal distribution with the same mean as the individual observations, right? And we'll talk about, you know, kind of why that is. The only thing that's different is that instead of sigma as your standard deviation, the standard deviation for an average observation is going to be sigma over root n. So what is this whole blurb? I'll just write it out in words here. X bar follows a normal distribution with a mean mu, right? And I'll just put in brackets here, that's the same as the individual observations. Same as the individual observations. And a standard deviation of sigma over the square root of n. Sigma is the standard deviation, right? And so what we do to try to avoid saying that the standard deviation of X bar is the standard deviation of X over root n, right? That's kind of how we would have to say it. We just call sigma over root n the standard error instead. So here, right, to simplify the standard deviation of the standard deviation over root n, we call this the standard error is sigma over root n. So if we take it back, what we're saying is that if we're sampling from a normal distribution, then the means from those distributions are going to be normally distributed as well. I don't think that's too crazy, right? Intuitively, if we think about collecting samples, we know that if we collect a sample of size 20, for example, and we're measuring heights across the college for, I don't know, just pulling a random example, right? So we're talking about the heights all across the college, and we collect a random sample of size 20. We calculate the average. We understand that the average that we found should be close to the population mean that we're trying to figure out what it might be, right? It's not going to be exactly there, but it's going to be close, right? And so as we collect more and more samples, right, because now we're starting to talk about a distribution of the means, has a normal distribution with the mean the same as the individual observations, right? There's no reason to think that a bunch of averages of 20 heights, right, is going to be that different from the individual heights at the college, right? And so, so they're all centered on the same value, right? But the thing is that if we're collecting averages, we don't expect that huge variation that we're expecting in individuals, right? We know that there's shorter people, there's taller people, and then there's kind of middle of the road, and we're all on there somewhere, right? And so what we have, right, if we're collecting a random sample of size 20, for example, from this group, well, we're going to get some tall people, some short people, probably, right? Even if we get kind of a weird sample and we sample, I don't know, really short people, right? They're going to make up kind of the tail ends of our normal distribution, right? And so what we're saying is the distribution of means so X bar, will be centered on the population mean for individuals, individual observations, I guess, I'll translate that into kind of what we're saying, right? We expect our sample mean to be close to our population mean, right? We expect our sample mean to be close to the population mean. That part is usually not so bad. The next part, though, is that, okay, well, if we're expecting all our population means, our sample means to be close to our population mean, that means that we have less variability. In fact, that variability depends on the sample size, the size of the sample that you're collecting, right? And so that's why we have to adjust. So we're going to take sigma, the standard deviation for a single observation, right? And I'll put that on here, that this sigma, this is sigma from a single observation. And n is your sample size. So depending on how large these samples are that you're taking, right, it's a little bit confusing because we have to think about, okay, well, I only collect one sample, right? I'm not going to go out and collect, 4,000 samples of size 20 from the college. That's crazy, right? What we're developing here is the theory behind why I only have to collect one sample is because I can then assume that it follows a normal distribution centered on mu, right, the population mean, and has a standard error of sigma over root n. Right? So we'll only, at the end of the day, we'll only collect one sample, but the reason is because we know that that sample mean is going to follow a normal distribution. Right? And so that's what we're talking about here. Okay, so it's going to be centered on the same population mean. The spread will depend, or the spread, and I'll just say the standard error in this case, which is sigma over root n, will depend on the sample size, right? Because if we think about our sample size and what it does for our sample, right, the larger our sample is, the more confident we can be in that estimate being close to the population mean, right? And so if we're taking a large sample, then our standard error is going to be small, right? We're dividing by root n, and so then our spread is going to be quite small. So the spread, the standard error, which is sigma over root n, will depend on the sample size n. As n increases, right, as you take a larger sample size, the standard error decreases. So kind of, in other words, larger sample sizes are expected to yield means that are closer to the population mean. So larger sample sizes are expected to yield sample means that are closer that are closer to the population mean. So what's going to happen here, right? If we go back to this chapter 6 example, because like I said, all these problems that we're about to do will start the same way. They'll establish, okay, you've got a normal distribution with a mean this and a standard deviation this, right? Then you can do those parts with the individual observations, and then it'll follow it up with, okay, now you've taken a sample of size 45, for example. Right? Now, what's the probability that you find an average weight less than some amount? Right? And so if we go ahead and kind of refer to this again, it's going to be in here a couple of times, I guess. Oh. And P. Just because I'm talking about it a lot. So here we've done A, B, C, D, E, right? But what we said, right, from these parts is, okay, we've got normal distribution, individual observations, follow normal distribution centered on 16.3, and sigma is 0.2. So this is the distribution for individual observations. Right, and we use this curve to find probabilities, right? The area under the curve is the probability that you're looking for, bless you. So now what we're saying is, okay, well, part, bless you, bless you. Well, side note, they sent out an email saying that we should be prepared to do remote delivery, but I already do remote delivery, so we'll just meet on Zoom if we're all quarantined. Okay. Not getting out of this class, no, no, no. So, a follow-up, right, another part would say something like, you collect a random sample, of size 45. I'm making it as kind of generic as possible, right? Because this is just how it's always going to be, right? It tells you, okay, you collect a random sample of this size. That's just a statement, right? There's no question here. So what I would usually say, just to warm you up and just to kind of alert you to the fact that, okay, we're actually talking about a mean observation here, I would say, what is the sampling distribution? What is the sampling distribution of the mean? The sampling distribution is that X bar follows a normal distribution with a mean mu and standard deviation sigma over root n. So all we need to do is we need to plug in the appropriate values. And so the only things that we know and need to know are mu, sigma, and n. And so what we would say to answer this question is we would say X bar follows a normal distribution still centered on 16.3, right? Because that's the center for all the individual boxes. There's no reason to think that if I collect a sample of size 45, that it should be centered on anything other than 16.3, right? And so 16.3 and then comma with a standard error, right, of sigma over root n. In this case, sigma is 0.2 and root n is root 45. You can leave it like this, right? Or what we can do is we can do 0.2 divided by the square root of 45. Or X bar follows a normal distribution with a mean of 16.3 and a standard error of 0.0298, rounding to 3 decimal places, or 4 decimal places. Decided to keep a couple, otherwise the rounding gets a little bit weird, right? But what's kind of cool, right, is, okay, so now, just ignoring that this is about X bar, we know what this looks like, right? We know that it's centered on the same thing as the original observation, the individual observations, but our spread is quite a bit less, right? Our spread for individual observations was 0.2, but once we take into account that we've taken a sample of size 45, then essentially how stable do we expect these means to be, right? How tight around our population mean do we expect these things to be? Pretty tight, 0.0298, right? Now, if you know something follows the normal distribution, you know the mean and you know the, let's call it standard deviation, right? This is the standard error because it's for the mean, right? But what we can do is we can calculate z-scores, right, to find probabilities. And so now, we can use this information to calculate probabilities using z-scores. So, do we have it on here? Yeah. So on your formula sheet, right, it's going to be there, but even if you don't have it, right, it's not that crazy. Z equals, instead of X, we're talking about X bar minus the mean, which is still mu, right? How far is your sample mean from mu, your population mean? And then over sigma over root n. Sigma over root n is going to be one number. And so that's on your formula sheet, right? It says, so you've got the normal distribution on the right-hand side, the normal distribution, and you've got the standardized z-score, and then the sampling distribution, z equals x bar minus mu over sigma over root n. Right. Once you have a z, well, then that z behaves the same way as all the other z's, right? You can go to the z table and you can find areas under the curve. So after we have found z, we use it to find probabilities. The same way we did for individual observations. Individual observations. So what I want to do, just to illustrate what's going on here, is I want to steal the example here. Might actually be if we look at part C, right, what proportion of boxes will weigh between 16.11 ounces and 16.61 ounces, right? If I just steal this, and we'll reword it for a mean. So what proportion of mean weights, I guess this was part F, so this must be part G, seamless. What proportion of mean weights are between 16.11 ounces and 16.61 ounces? So now, right, nothing changes about how we approach this problem. It's just we have to be kind of alert when we're reading these parts now, because it'll either be about, well, what proportion of boxes, so individual boxes, are between these weights. And now we're talking about, okay, what proportion of mean weights, right? So as soon as you see that word mean in there, then you're thinking, okay, I have to take sigma over root n as my standard deviation. And so, but also in the problem, right, I'm going to make you do individual proportions, observations, right? And then I tell you, okay, you collect a sample of this size, right? Then you assume that you have a sample of that size, and then I get you to do probabilities for means, right, after that. So I wouldn't be mixing them up or anything, right? It'll just kind of follow the same blurb. So now we're talking about mean weights, and mean weights, we said, follow a normal distribution centered on 16.3 with a sigma over root n of 0.0298. So if I want between 16.11, I'll put that somewhere here, and 16.61, somewhere around there. I want to know what that area is. So same thing that we did before, right? We're going to calculate z-scores, and then we use the z-table to find these areas. So if we call this x lower, but now it's an x bar, right? Because we're talking about a mean, and this is an x bar upper, just so we can kind of keep track. You don't have to label them like that, but because I'm going to be calculating two z-scores here, it's easier if I kind of label them somehow. So z for my lower is going to be x bar lower minus mu over sigma over root n in general, right? So put it on a fresh page here. My z lower is going to be 16.11 minus 16.3 over 0.0298, or if you wanted to just use sigma over root n and keep all those decimal places, that's fine too, but I'll just use the shorter one. So I've got 16.11 minus, minus 16.3 divided by 0.0298. Rounding to 2 decimal places, I get approximately negative 6.3 Well, I guess I'll write out all mine so you can check your work, but 375838926. But we already rounded that standard error, so yours, if you keep all yours, then it'll be a little bit different, right? Z, we always round to 2 decimal places, so we have -6.3. Skinny 8. Doing the same thing for the upper. Z upper is x bar for the upper minus mu over sigma over root n. Notice the anatomy of this thing, right? If we're talking about Z scores, we've got x minus mu over sigma. You notice just how Z behaves, right? X has a standard deviation of sigma, right? X bar has a standard deviation of sigma over root n. Right? We just give it a different name because it gets confusing, right? And so if you're talking X bar here, then you better make sure that you have sigma over root n here. If you're talking about an individual observation, then it's fine to just talk about over sigma, right? And so they're definitely related. And you just need to keep track of if you have an individual observation or a mean observation. I'll delete this because otherwise it might not make sense. Okay, so the Z for the upper bound is 16.61 minus 16.3 over 0.0298. I get 16.61 minus 16.3 divided by 0.0298. I get roughly 10.40268456. So to 2 decimal places, 10.40. If we're talking about probabilities, right? Does anyone remember what, I think I can go back and find it. Was it last day or the day before? That we did these calculations. It's the day, it's a while ago. Crazy. Oh, here it is. So individual boxes, we found that the probability of having an individual box that's between 16.11 and 16.61 ounces is 0.7683, right? So we found kind of a reasonable sounding probability here. In fact, I'll steal this. And kind of put it in a dreaming bubble. Not much of a bubble, just a squiggly. Right. The proportion of, and then I'll add in here, individual boxes. Just to emphasize that this is from before. We found that probability to be 0.7683. Right? We can find that probability. In fact, even though it looks like it's going to be hard to find this probability, it's actually very easy to find the probability of being between -6 and +10. It's approximately 1, right? So here, if we think about our mean weights, or actually, let's talk about X, individual observation X, just so we can do the side-by-side comparison. we found that between 16.11 and 16.61, this area was about 0.7683 versus, and now I'm going to do the same thing but for the mean observation. So now I've got X bar. So now I've got a mean. Well, X bar says that 16.11, 16.11 is negative 6.38 standard deviations below the mean. So somewhere way out here, I've got a Z equal to negative 6.38. Yep. Is X bar equal to 16.11? Right, so way out in the tails. And even further out in the upper tail, right, I've got Z equal to 10.40, which is also X bar equal to 16.61. Because the means are pressed together, right? They're all hanging out around the population mean, which is here at mu. Right? All these things are closer together. These cutoff points, right, are at the same values, right? But now, when I'm talking about means, right, the probability of being in between here, right? Once we're out in the tails far enough like that, we can just say that this area is approximately 1. For this area. So we can draw this another way if we wanted to compare these things. If we've got the same scale, right? If I've got 16.11 here and 16.61 here, and then I've got that going on down here as well. 16.11 and 16.61. Get it off that page break here. Hang on. There. If we're talking about an individual versus a mean, because now I've got these guys, well, pretty much lined up, right? 16.11 and 16.61. An individual has more room on the outsides of this thing. Whereas the mean is kind of more, oh, that was a terrible one. Right. I want most of my distribution to be taken care of already, right? Because they're smushed more together. So means are closer. Means as in X bar are closer to mu. Just more compressed. So we always expect the probabilities to be if we're looking at something like this, right, the probabilities of a mean being between 16.11 and 16.61 is a lot larger than for an individual observation. Okay, cool. What did I want to do? Just make sure I didn't forget to say anything, blah, 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 blah. Okay. So one, pretty cool thing is that, okay, so we've been saying, fine, we take from a normal distribution, we expect our means to follow a normal distribution. What's pretty cool is that as long as we have a large enough sample, it actually doesn't matter what distribution we're taking from. So we can sample from skewed distributions and the means will still follow a normal distribution. But that doesn't make sense. It does. So here's an LFF, a little fun fact. The sampling distribution of a mean, X bar, will always follow a normal distribution. Will always follow a normal distribution. I'll put comma, assuming we have a large enough sample size, or assuming our sample size is large enough regardless of what distribution we're sampling from. Regardless of what distribution we sample from. What does this mean for us? This means that we don't have to have a normal distribution that we sample from. We're able to sample from a skewed distribution as long as we make sure that our sample size is large enough. We'll kind of touch on that in a little bit here. As long as our sample size is large enough, we can still use this formula, right? Z equals X bar minus mu over sigma over root n. Because we can assume it follows a normal distribution. Okay, so what does this mean for us? This means we can sample from any distribution right? And I'll put a couple just to kind of jog your memory, right? You can have a skewed distribution, bimodal distribution. Yeah, we'll make room for a normal distribution. So this means we can sample from any distribution and still assume X bar follows a normal distribution. If n is large enough. We are going to be talking a lot about n, so at this point I'm expecting you to remember that n is just the sample size. So n is large enough. How vague is that? It depends on a few things. Sometimes we can only afford to have a sample size of 20, for example. Then I would argue, okay, well, nope, that's large enough. I'm gonna assume that I have a normal distribution for my means. Not necessarily true, right? But that's an assumption that I have to make. So that n is large enough condition, typically we say n larger than 25, 30 is big enough. Right? And so if n is large enough, if n is larger than 25 or 30, I've seen articles in journals where they've pushed for 15 being large enough. At the end of the day, it just depends on how normal the distribution was that you were sampling from, right? So if you can assume that you're sampling from a normal distribution, then we can draw down that number, right? And so if we can assume that we are sampling from and I'll even say just not necessarily normal, but a unimodal symmetric distribution, from a unimodal, so only one hump, unimodal symmetric distribution, usually that means the normal distribution. You could even have a uniform distribution if you wanted to, but we wouldn't really talk about the average there anyways. So usually we're talking about the normal distribution, right? So if we can assume that we're sampling from a unimodal symmetric distribution, we can assume the mean follows a normal distribution. I'll use capital N just to emphasize that it's a name. Assume that the mean follows a normal distribution for sample sizes as small as n equals 15, for example. Right, so it just depends on how skewed the distribution is that you're sampling from. For example, if we talk about income is this kind of classically skewed in the right direction distribution. So if we're sampling from income looks a lot like this, right? Most people are down here, and then, a few people are up in the higher end, right? So here we would need to sample our larger sample to get our mean to follow a normal distribution, right? Versus if we talk about, heights like we did earlier, for sampling from a distribution that's already unimodal and symmetric, although that one's kind of looks like it's running away. There. So here, for income, we would need n greater than or equal to 25 or 30, for example. And here we would need n greater than or equal to 15-ish, right? Because we're already coming from a normal distribution, so for it to morph into a normal distribution isn't going to take that much.
population that's super small, like say a rare disease or whatever?
Yeah, so if the population is small, it's trickier because then it's hard to know what the distribution is, and you don't want to oversample either. So there's this kind of fine line that we get into later. So not for these problems, but later on, especially in chapter 9, I want to say, then we get into this kind of fine balance of, okay, we want a large sample, large sample, large sample. And that's probably what you came into this course knowing, right? Well, as long as I have a large sample, right, that's good. But there's also that kind of switch over where if our sample is too large, then we can't assume that these observations are independent anymore, right? Because we're going to have siblings, we're going to have, you know, related people in here, especially if we're talking about something genetic, for example, if we're talking about, you know, diseases and things like that. So it's a tricky area. But that is something that we will keep in mind later, that we want large samples, but not too large. Roughly less than 10% of the population is the kind of cutoff. Yeah.
Just going back to like the approximately one answer, will that kind of always be the case for the
Often, just because the means are so much closer together, right? But as a fact, the probability for the means is going to be a lot larger than the probabilities for individual observation, right? And so it's not necessarily always going to be 1, right? It could be, you know, 0.9987, something like that. But it's always going to be a larger area than for individual observations. Yeah. Cool. All right. So now that we've kind of talked about, okay, we know the distribution of the mean observation, what I want to do kind of quickly here is start into 7.2, which is on confidence intervals. So in 7.2 and 7.3, and the rest of chapter 7 will kind of, I'll leave for you to read. We're going to focus on 7.2 and 7.3 because what we're doing here is we're developing these major ideas that we'll use throughout the rest of the course now. So what we're going to be doing is we're going to be finding confidence intervals and doing hypothesis testing, which is what we'll get to in 7.3. Right? So hypothesis testing is this kind of multi-phase thing that we do, right? But that's the reason that you have to take this course, is so that you've been introduced to hypothesis testing in various forms. So we'll start with confidence intervals because, well, that's how they fall in the chapters, but also it's just a little bit easier to wrap our heads around. So confidence intervals, we actually use confidence intervals a lot in kind of everyday life, right? And so if I asked you, okay, how far, how long is this board from here to here? We could measure it, right? We could go through, I've even got a yardstick, but I'm not going to do that, right? We could go through and we could measure it, but if I'm asking you and you have to stay there, you would give me your estimate, right? That's your best guess at how long this board is, right? That's essentially your sample mean, right? And so your estimate is your sample mean. That's your best guess at what the population mean might be, right? And so the actual distance of the board, I want you to think of that as the population mean, okay? Because there is some actual distance there, We could measure it. We could get as precise as we wanted, right? But it exists, it's some number, right? Our estimate is often pretty good, right? We've got an estimate in our mind, and that's going to be our sample mean. We understand that our best guess is not going to be exactly right? But depending on how confident we are, right, we're going to put bounds on that, right? You would say something like, oh, now I'm really bad at judging distances and kind of lengths and stuff. So I would say that this thing is probably 3 meters. I've got the upper hand here. I can even face it out. 1, 2, 3. Yeah, I feel pretty good about it. Right? So 3 meters plus minus a meter. Right? Give myself lots of room. Right? And you guys understand that if I say plus minus a meter, I'm not very confident in my estimate, right? Because I'm giving myself a huge buffer there. If I said 3 meters plus or minus 10 centimeters, you guys would be like, whoa, she's pretty confident, right? Because I'm saying plus or minus 10 centimeters, my estimate's in there, right? And so what we do is we develop confidence intervals for our estimate, which is our sample mean, right? So now we're gonna have, okay, fine, I collected my sample. I understand that my sample mean is not gonna be my population mean, but I can be pretty sure it's close to there, right? And so what we do is we use math to develop these bounds that say, okay, based off of our sample and what our standard error is, this is where I expect my sample mean to be in relation to my population mean. Okay, so confidence intervals. Confidence intervals. I like to think of it as builds bounds. So builds bounds. So many S's. Confidence intervals build bounds. There we go. Sounds better. Confidence intervals build bounds. Oh, say that 10 times fast. Around our sample estimate. For now, we're going to talk about X bar as our estimate, but we're actually going to change that, right? And so here we're just developing the core concept of a confidence interval and using just one sample mean as our kind of our guide, right? But then for the rest of these chapters, I'm going to say, okay, now we're talking about this type of situation, right? The difference between two means, for example, we can build confidence intervals around that. We're going to move into proportions, right? Move into the difference of two proportions, right? And so we're going to use it for a lot of different scenarios, but the idea stays the same always. So confidence intervals build bounds around our sample estimate. To communicate how confident we are in having captured the population proportion, right? That's in general, but in our case, if I'm talking about the sample mean, the population equivalent would be mu, right? And so our confidence interval is always trying to capture our population parameter, not proportion. Population parameter, that was a biggie. a big screw up. Yeah. I fast forwarded to chapter 9. Yikes. So a confidence interval at the very basics is going to have this form. So it's going to be the estimate plus minus the margin of error. So if you think about, okay, we're measuring this board, right? Your estimate, that's your best guess. And then your margin of error is that kind of buffer that you apply, right? Plus minus because you want to go down a little, up a little. Right? And so here, I call this your buffer. Just the kind of, oh, that doesn't read very well, does it? Oh, looks the same. Right. Just to kind of, okay, you've got this little buffer zone. That's your margin of error. Right. And so what happens is in the case of one sample mean, and if you flip your formula sheet, then you'll see the top portion of the formula sheet is all confidence intervals. And it's all those confidence intervals that we're going to talk about, right? And so, but they all have that same form of some estimate, right, from our sample. And so this is from our sample. And then plus minus some chunk. So in the case of one sample mean, X bar, and I know if you're kind of scooting ahead here, we have two scenarios, one where sigma is known and one where sigma is unknown. In chapter 7, we're pretending to know sigma, right? But just because it's more stable, it's a more stable situation. If you think about it though, sigma is your population standard deviation, right? And so that would be, well, here we're only measuring one thing, so it doesn't really make sense, right? But your population standard deviation assumes that you've had the whole population in your grasp to be able to calculate that. And then now we're trying desperately to figure out what mu might be. That doesn't make sense. You're saying you had the whole population and then you just let it go. And now you're trying to desperately sample to try to figure out what mu is, right? It's kind of an unlikely thing that might happen, right? So later on, what we say is, oh, we don't actually know sigma. I'm just going to use the standard deviation from my sample instead. But now I'm estimating that standard deviation as well. So it adds another element. So here, just kind of as training wheels, we say, okay, we're pretending to know sigma, right? Let's just pretend to know sigma for a more stable environment until we've got all these foundation things figured out. And then we say, that's never gonna happen. But now you've got the tools and we can just kind of tweak some things, right? So if you have a look at your formula sheet, it doesn't look that different, right? Z's turn to T's, sigma turns to S, which is your sample standard deviation, right? But things don't really change that much, right? So just as a kind of a roadmap of where we're headed, right? We're not always gonna know sigma. Right? In fact, at the end of chapter 7, we're gonna stop knowing sigma anymore. So in the case of one sample mean, and I'll say sigma known, right? Just to emphasize that later on, that's not necessarily the case, but for now it is, then our estimate is going to be X bar, right? And what are we estimating? We're trying to estimate mu, right? The population mean. We're estimating mu. So it's important to keep that, that link in mind too, right? I've got my estimate. Estimate of what? Estimate of mu. And then our margin of error, in this case, is going to be Z star times sigma over root n. Oh, got all blurry. Sigma over root n, we know from before, right? From just earlier, we said that, okay, well, sigma over root n, this is our standard error. The only thing that's new is our Z star. What happens is I want to say something like, I'm 95% confident that this interval captures the population mean, right? I'm 99% confident. So that Z star is what we call a critical value. Z star is a critical value. And how we find it is, well, we've only got the Z table so far. There's an easier way that's kind of shortcutted on the T table, but I'll bring those for you guys next class. I don't think I only have Z tables for you guys. So for us, what we need for a 95% confidence interval, what we're doing, whoops, and 95 is the default, which I'll also add a note here. This is the default confidence level that we use. Default confidence level. So what we have is that there's going to be some negative Z star and some positive Z star. And for a 95% confidence interval, this area here is 0.95. You've actually had to find this before, right? So 0.95 means that this area out here is 0.05 divided by 2, which is 0.025. And because I'm out of time here, this is negative 1.96. So negative Z star is negative 1.96 and Z star is 1.96. If I just sneak that last minute of your time, right? 1.96 is pretty close to 2, right? So essentially we're moving up 2 standard errors on either side of our estimate, right? 68, 95, 99.7 rule. They're all linked. And it's our job to untangle them. All right, nice work. See you guys on Wednesday. Bye guys.